So the first thing that happens in this problem is that we have a block of mass m with a spring of force constant k on top of it, and another block of mass m is placed on top of that. And we're asked what distance delta x the spring is going to be compressed so that that top block stays in equilibrium. Now, when that block is in equilibrium with the spring, we know that the spring is pushing up with exactly the gravitational force mg that's pulling it down, because otherwise it would have to be accelerating in one direction or another. So this tells us that k delta x equals mg, and that delta x is equal to mg over k. So that gives us our answer for part A. Now for part B, we're told that the spring is pushed down so that it is now compressed in extra distance d, so we have delta x plus d, and then it's released, and the block springs up some distance above its rest length, delta x over 2, such that the normal force is equal to 0. That block, that bottom block, just barely lifts off the ground. And now we're asked to find what this d is going to be such that this will occur. Now in the second part, we actually already know what delta x over 2 is, because it has to be exactly this value. Because remember, we already found that k delta x equals mg for a delta x of that value, and this spring needs to be stretched just enough that this block will be pulled up with the force mg so that the normal force vanishes. And so this tells us that first, delta x2 is equal to delta x is equal to mg over k. Now what we're going to do is we're going to set this height to be 0, and we're going to conserve energy from this initial position to this final situation. And we can do this because both springs and gravity are conservative forces. So in the initial situation, we have the spring potential energy 1 over 2 k times delta x plus d squared. And in the final, we have 1 over 2 k delta x squared plus the gravitational potential energy of the second block, which is going to be mg times 2 delta x plus d, because it first has to raise this extra distance delta x plus d, and then this delta x2 equals delta x above that rest length. Now we can square out this term so that we can simplify the equation. We get 1 over 2k delta x squared plus 2 delta xd plus d squared is equal to 1 over 2k delta x squared plus mg 2mg delta x plus mg d. Now I'm going to cancel out this term with this term because the 1 over 2k distributes, and then I'm going to pull the mgd over here and multiply through by 2 over k. So that gives us d squared plus 2 delta xd minus 2 mgd over k, because I had to multiply through by 2 over k before pulling this over, is equal to 4 mg delta x over k. Now if you'll remember, we know what delta x is. It's mg over k. So we can plug this in here, and we get d squared equals 2 mgd over k minus d squared plus 2 mgd over k minus 2 mgd over k is equal to 4 m squared g squared over k squared. Now these two terms are going to cancel, and we get for our final answer, by taking a square root, d is equal to 2 mg over k. So that's going to be the extra distance d that block is going to need to be compressed so that the energy in the spring is enough to pull this block up to the height at which this block will just barely lift off.